Welcome to CPE 350, Chapter 7, Binary Mass Diffusion. In the first section, we'll cover Fick's law and the governing equation for mass diffusion. For the whole chapter, we'll be working with Fick's law and learning to use the various molar and mass forms of it. We'll derive the equation of continuity, which is just a mass balance, and we'll be applying similar techniques to what we learned in the previous chapters to solve steady state and transient mass transfer problems. All right, so we'll start with Fick's law for mass diffusion. And this writes the mass flux, which is the kilograms of a species A per area per time, as a function of density, diffusivity, and weight fraction. So DAB is the diffusivity of A and B. In order to have mass diffusion, you need at least two substances, A and B. You can't really have A diffusing in a vacuum because then you just have sort of a pressure volume expansion problem. So there's always at least two species, oftentimes many more. So the binary diffusion coefficient is either the diffusivity of A and B or B and A because they're mathematically identical. And it has the same units as thermal diffusivity, which is meters squared per second. So whenever you see a dimension with those units, you can assume it's related to a diffusivity. It comes up also in conduction, electronic conduction. Rho is the bulk density of the composite of A and B, whether it's gaseous mixture or a solid composite. It's two species, and so it's the bulk density of their combined amalgam. And finally, we've got the mass fraction of species A and the rate at which this mass fraction is changing with respect to the spatial coordinate is the derivative we're looking at. We're going to think a little bit more about what this bulk density means because it's slightly confusing. So when we talk about the density of species A, we're not talking about the pure species density. We're talking about the density of A within the composite. And so as an example, here are some images from X-ray computed tomography of a lithium-ion battery cathode. And so on the left-hand side, the white spots you see are areas of high electron density, and that's the actual cathode particles. And these are nickel, cobalt, manganese battery cathodes. Everything that's sort of gray is this low molecular weight domain that combines carbon black with a polymeric binder, and so it doesn't scatter a lot of electrons, and that's why it appears dark. So we'll consider those as the two phases of our composite. And on the right-hand side, you can see that the computational tomography has highlighted some of the actual cathode particles, and they're all different colors based on their orientation. But what we're looking at when we talk about the density of species A is the density of those particles in the total volume of the cathode. So if we say that the particles are species A and the gray stuff around it is species B, and we also define the length of one of these cubes as L, we can write the density of A in this composite as the total mass of all the particles over L cubed. Another way we can look at that is the total volume of all the particles times the pure species density of A. So that gives you the total mass of all the particles. And again, that's over the total volume, not just over the volume of A. So hopefully this differentiates what a subscripted density means. It's more of a concentration than what we would normally talk about as a material density. All right, so how do we define density then? That means it's the mass average density. So it's the mass fraction of A times the pure A species density plus the mass fraction of B times the pure B species density. Whenever there's binary diffusion, both A and B are present, so you've never got a single species. So your density is always going to be a composite bulk density. Okay. So now let's look at Fick's law for molar diffusion, and it's quite similar in form, but in this case we use a capital J, and that represents the molar flux of A, moles per meter squared per second. We no longer need a density here, we just have the diffusivity of A in B, Again, in meters squared per second, this is identical to the diffusivity of B in A. And finally, we have the concentration of A, and the concentration spatial gradient, dCA dx, is the driving force for diffusion in this instance. So what's the relationship between the diffusivity for the molar form of Fick's law and the mass form of Fick's law? Let's have a little look at this. If we start with Fick's law for mass diffusion, just write it as is, and then we simplify it slightly using this definition of a species-specific density. Again, the density of A in the composite of A and B. So we can simplify Fick's law for mass diffusion as a density gradient. And now we can divide both sides through by the molar mass of A, which we'll call capital M, subscript A. And on the left-hand side, we'll just divide. On the right-hand side, we'll specifically divide the numerator by this molar mass. On the left-hand side, our units cancel out, and we see what we have is actually just a molar flux. On the right-hand side, again, the kilograms of A cancel out, and the units we have are moles per meter cubed, which are units of concentration. So we see that we've changed the numerator to a concentration. And at this point, Fick's law of diffusion is exactly identical to what we would write for the molar flux. And that basically means that because you can convert between the mass flux and the molar flux, DAB is the same exact value for both. So the value of DAB isn't going to change depending upon the expression that you use. The last thing we're going to do is define the governing equation for mass diffusion. So this is basically just a mass balance. We'll choose a Cartesian coordinate system and we'll look at an element that has differential dimensions in x, y, and z. So three-dimensional mass diffusion. And we're going to be using variables that relate to mass rather than moles, because during a chemical reaction, the total moles of molecules are not conserved. The total moles of atoms are, unless it's a nuclear reaction. But to avoid that ambiguity, we're going to work with densities. So we have our usual equation that accumulation is the flux in minus the flux out plus any net generation within the unit. And again, we're using density. So on our accumulation term on the left-hand side, we've got the density of A times that differential volume divided by the change in time. So that's the rate at which accumulation is occurring. And then on the right-hand side, we've got our flux terms for x and y. So that's the flux in at x and the flux out at x plus delta x. And then we multiply the area through which mass is fluxing. So for x, that area is delta y, delta z, and so on and so forth. So we do that for each of our dimensions. And then finally, we include a generation term where RA is the rate of mass generation per volume. And so we multiply that then by the differential volume. So this is our governing equation, and we're going to turn it into a differential equation by dividing through by delta x, delta y, delta z. So as we cross these terms out, we see that all of our x flux terms are then divided by delta x, all of our y flux terms are divided by delta y, and so on. So it starts to look like the definition of a derivative that we're familiar with. We can take the limit as delta x, delta y, delta z, and delta t all approach 0, and we get the differential equation form of the governing equation. There's a lot of repetition of the j terms, and so you can kind of guess what we're going to do. We're going to use vector notation to simplify this, in that d dx of a vector is known as the divergence. It's written as a del dotted with the vector. In this case, the vector is JA. And that's just a simplification, and also enables us to more generally write the governing equation in different coordinate systems. You would just have to expand that divergence in either cylindrical or spherical terms. This equation is quite accurate and powerful, but it only applies to problems with diffusion. in which we don't have any advection. So no flow is moving the mass. It's only random diffusion. We'll introduce flow in the next chapter. Thank you for listening, and I'll see you for example 13.